be less than, it's below the demand for food, and therefore there will be famine. Of course, as it turns out, Malthus was incorrect. There are a lot of reasons for that. You can consult your history books. But the fact is, he was dealing with a system of two linear equations. That is, two lines, one which represented demand, one which represented supply. He was concerned about the intersection. Let's talk about intersection for a moment. If you are standing at the intersection of Main Street and Broadway, what does that mean? Well, first of all, hopefully you're not standing there because you're probably getting run down by a car. But if you were, if there were no cars present, and you were standing at the intersection of Main Street and Broadway, it would mean you were standing at Main Street, actually in Main Street, and also simultaneously standing in Broadway. You were in both streets. The intersection point for two lines is where the two lines cross, and that point, the XY ordered pair, would be the only ordered pair that would work in both of the equations, the only ordered pair that would be on both lines. Now, what we're going to do is we're going to take two linear equations and find out how we can solve them. For example, let's go to the board here and look at these two linear equations. Y equals 3x minus 4 and y equals 2x plus 1. We're concerned about here is where those two lines cross, the value of x and y that will work in both equations. And we're going to first attempt to solve this system of equations by graphing. So let's look at the next visual. And the next visual shows us the two equations and the graphs of the two lines. Which line do you think is y equals 3x minus 4? Is it the red line or the blue line? You should have said the red line. The reason is very simple. The red line has a steeper slope. Notice that y equals 3x minus 4 has a slope of 3, while y equals 2x plus 1 has a slope of 2. Also, the red line has a y-intercept below the x-axis. And of course, the intercept for y equals 3x minus 4 is negative 4. But the important point here is where the two lines intersect. They intersect at the point 5, 11. X equals 5 and y equals 11. Which means that 5 for x and 11 for y is the only ordered pair that will work in both equations. As always, we're going to check. And we check by plugging in 5, 11 for x and y into both equations, which is seen on the next visual. And that visual shows us that we plug in 5 for x and 11 for y, and 11 equals 15 minus 4. That checks. And then we plug in 5 and 11 for x and y equals 2x plus 1. 11 equals 2 times 5 plus 1. That also checks. We must check in both equations. And indeed, we have now found that the point x equals 5, y equals 11 is the only solution to our two equations. We have solved the system of equations graphically. Okay, let's take a look at the next visual. The next visual has a real problem to it. Y equals 2x plus 3, and 3x minus 5y equals negative 1. What kind of problem might that be? Well, if you look at that second equation, if you got to get that second equation into y equals mx plus b, the slope is going to be a fraction. As I mentioned in earlier lessons, I don't like fractions. You might not like fractions, and graphing fractional slopes sometimes gets really confusing and leads to errors. So we need to find a better way to do that. And the way, other than graphing, to solve systems of linear equations is a method called substitution. Notice that the first equation in our visual is y equals 2x plus 3. We have y directly in terms of x. And therefore, as seen in the visual, we can exchange the y in the second equation and make it into 2x plus 3. Since y equals 2x plus 3, we can replace the y with 2x plus 3. Just as if I gave you two $5 bills for a 10, that's fine. The two 5s would replace the 10. It's a valid substitution. So on the third line on our visual, we see 3x minus 5, parentheses 2x plus 3, close parentheses, equals negative 1. We've taken the second equation and replaced the y with 2x plus 3. Now we're back to where we were early on in this series of lessons. We're solving an equation with parentheses. We multiply through, combine like terms, and divided by the coefficient -7 to get x equals -2. My obvious question now is, what are we going to do when we solve x equals -2? Some of you may say it's time to check, and you would not be quite right. Because remember, when we're solving a system of equations, we're solving for an intersection point. And that point has both an x value and a y value. We cannot check until we got a complete solution. A complete solution here would be x and y. So, let's look at the, let's not look. Let's take a look at what we need to do first. And what do we need to do? We need to plug in the solution, which is x equals -2, into our original equation y equals 2x plus 3. Okay? And now we can go ahead and look at that visual to see how we do that. And it's really quite simple. We've simply replaced the 2 with -2 and solved for y. We get -1. And the last line on the visual shows us the ordered pair -2, comma, -1. X equals -2, y equals -1. Now that we have a solution, now it's time to check. And we're going to check by replacing the x and the y with -2 for x and -1 in both equations. I must emphasize, we must check in both equations. The next visual shows us that. We've replaced the 3x minus 5y equals -1. That is the one of the original equations. We replaced the 3x minus 5y equals -1 with x equals -2 and y equals -1. And 3 times -2, -6 plus 5 is -1. That checks. Now the question is, I said checking in both equations. We could go back to the equation y equals 2x plus 3 and check that. But indeed, since we used that equation to solve for the y, the -1, when we had x, there really is no need to check. If you want to, you can do that, and you could check in both equations. But since we used the original equation, y equals 2x plus 3, to solve for y when we knew x was -2, there's no need to check in that one. We must check in the other original equation. And as we saw on the visual, it did check, so we know that -2, -1 is the only ordered pair, the only value of x and y that works in both equations. There are many, many values of x and y that will work in one equation, but they will not work in the other equation. This is the only ordered pair that works in both. It is indeed the intersection, and therefore is the solution to our system of equations. Let's take a look at a second substitution problem. In fact, let's go ahead and look at the next visual. The next visual gives us this problem. 2x plus 4y equals 2, and 5x minus 2y equals 17. Now, what's different about this problem? What's different is we don't have one of the two problems written as y equals a function of x or x equals a function of y. To do substitution, to use the method of substitution to solve a system of linear equations, we must be able to get one of the equations in the form x equals a function of y or y equals a function of x. So notice the arrow shows you in this visual that we've taken 2x plus 4y equals 2 and written it as 2x equals -4y plus 2 by subtracting 4y from both sides, divided everything by 2 and getting x equals -2y plus 1. We now have x in terms of y. This method is called substitution because what we're going to do is substitute that function of y for the x in the other equation. The other equation being 5x minus 2y equals 17. So if we look at the next visual, we'll see that we replace the x with parentheses -2y plus 1 because we just saw that that was what x was equal to. And now we have an equation with one variable, one letter, y, and we've Multiply through the parentheses, combine like terms, we get negative 12y equals 12. Dividing by negative 12, we get y equals negative 1, which is the solution for y. We have not yet gotten the solution for the system because we need to get the value of the other letter, in this case x. The next visual shows us how to do that. X equals negative 2y plus 1. That was something we found out, and therefore we replace the y with negative 1, and x must equal 3. Thus, our ordered pair is 3, negative 1. That's the solution. X is 3, y is negative 1. Now we need to check. I want you to remember something I said. In the previous problem, I only checked in the one equation because the other equation, we used the original equation to obtain one letter given the other. Here, remember, we did not do that. We modified one equation to get